So here's the last big topic, okay? And it's kind of the culminating thing of everything that we've led up to this point, okay? So you've got to be able to write chemical formulas. You've got to be able to balance equations. You've got to be able to do mole conversions, okay? And most importantly you have to pay attention to detail, and you have to follow through, like you do this, you do this, you do this, okay? So stoichiometry in and of itself isn't horribly difficult, okay? Where you run into trouble is when you try and shortcut the process, okay? So if you try and look for shortcuts, this is where this is going to be a train wreck. Because we're going to end up doing conversions that might literally, like when I write them out on this page, it's going to run from one screen to the other, okay? But like I said, we've laid a very, very solid framework for this. All we have to do is literally take all the pieces of everything that we have done and put it all together into this last unit. So this is why we always do stoichiometry last. Okay, so in terms of that packet, okay, that you all have, and you all have like the website and all that good stuff, or the link to that in your Google Classroom. If you want to use that as a resource, that's fine. Everything that I'm going to give you to do is going to be my stuff. So that way, in terms of what you can have that, it's there. There's some videos. If you want to work through them, great. But basically, everything that I'm going to give you to do is stuff that's mine. Okay, so you don't have to worry about you're not going to hand in anything out of that packet. Okay, it's there. It's a great resource. There's some extra problems you can do. It takes you through it step by step by step. I'm not saying don't use it. It's a great resource, but in terms of what you are going to hand in is all going to be stuff that I'm going to have you do. Okay, so you will not hand it in. It's just a great resource to have. Okay, so if you want to understand stoichiometry, we're going to start with making cheese sandwiches. Okay, because if you can figure out how to make cheese sandwiches, you can figure out how to do stoichiometry. Okay, literally, that's it. If we can figure this out. So we're going to make cheese sandwiches, and cheese sandwiches are going to be pretty simple. It's going to be a synthesis reaction. And it's going to be boring, okay? But we're going to start off, and we're going to have one slice of cheese plus 2 slices of bread. It's going to end up making B2S, okay? We're going to make a cheese sandwich, right? That's it. There you go. Now, and you sit there and go, well, that's fairly simple. And you're right, it is, okay? No, so think about this. I want to make, let's say you got a big family gathering coming up, and you want to make 10 sandwiches, okay? Mom says, hey, here's the story. Ella, I need you to make 10 cheese sandwiches. Ella's going, I'm on it, Mom, I got this, okay? So Ella, you're going to make 10 cheese sandwiches, right? How many slices of cheese are you going to need?
10.
10. Why?
Because you need 10 sandwiches.
Yeah. I need 10 sandwiches. Why do you need 10 slices of cheese?
Because you need 1 per sandwich.
Oh, by the way, have we started that? Okay. Yeah, because so there's a 1-to-1 ratio, right? For every 1 slice of cheese, that goes into making 1 sandwich. Okay? Congratulations, you just did stoichiometry. Okay? Emma, you're going to make 10 cheese sandwiches. How many slices of bread are you going to need?
1.
Why?
Because you need 2 slices of bread per sandwich.
Yeah. Okay? Congratulations, you just did stoichiometry. Okay? So, you'll get it. I just have to convince you that you know how to do stoichiometry. So here's the simple thing. These coefficients in this situation are representing like slices of cheese or slices of bread. In a chemical reaction, those coefficients are going to represent moles, okay? That's it. So this would be like 1 mole of cheese, which is going to react with 2 moles of bread, which is going to make us 1 mole of sandwiches, okay? Now, what you all just did is you said, oh, hey, I want to make, this is what you did. You just don't know this is what you did. You said, hey, I want to make 10 sandwiches. That's kind of cool, okay? So what you did is that you said, hey, I've got to make sandwiches. So I want to put sandwiches down here. It's the same process that we've done in all the conversions we've done up to this point. Oh, I'm going to put sandwiches down here. Okay, what do I want? Well, Ella was in charge of figuring how many slices of cheese that she wanted. Oh, so I'm going to put slices of cheese up here. Oh, okay, cool. Then, without knowing this is what you did. You said, oh, there's a 1 in front of the sandwiches. Oh, there's a 1 in front of the cheese. The sandwiches cancel out. I get 10 slices of cheese. That's it. Okay? That's it. That's how stoichiometry works. It's a ratio of the coefficients, right? Now, Emma's was a little bit more complicated. Okay? She said, oh, I want to make 10 sandwiches. And it's down here she's going to go, oh, for every 1 sandwich, I need 2 slices of bread. Oh, that's cool. Sandwiches cancel out. Guess what? She multiplied 10 by 2. She said, I get 20 slices of bread. Okay? That's cool. That's it. Literally, this is it. This is it. It's just ratios. That's all it is. Okay? Now, I want to change things up a little bit with Peyton. Okay? So I'm going to give Peyton, I'm going to say, Peyton, man, you got 30 slices of bread. Okay? Peyton, you got 30 slices of bread. How many sandwiches are you going to be able to make with 30 slices of bread?
15.
How'd you get that?
You take the 30 pieces of bread and you divide it by 2.
Fantastic. So this is what he did. He goes, oh, I got slices of bread. That's cool. For every 2 slices of bread, I can make 1 sandwich. The bread cancels out. I take 30 divided by 2. I get 15 sandwiches. Okay? So here's what I want you to, first off, when you look at Stoic. With Stoic, you can go in 2 directions. You can have products or reactants and figure out how much product that you need, or you can have product and figure out how much reactant that you need. Okay, cool, there you go. So I don't want you to think that Stoic only goes in one direction. I don't want you to think that, oh, you can only convert from reactants into products, okay? You can also convert from products and work backwards into reactants, okay? Now, so let's look at a chemical reaction. Okay, we want to make water. So what's the simplest way to make water? What can we combine to make water? Do not make this difficult. Look, Etheridge. What can I combine to make water?
Hydrogen and oxygen.
Yeah, we're going to take hydrogen and oxygen. We're going to make water. Okay? It's the exact same idea of sandwiches. It's the exact same idea. Okay? So here's one way that you can look at this. You can sit here and go, okay, hey, I want to make water. All right, so let's make water. So, we're going to make water. Okay, we're going to go to the kitchen. We're going to go to the chemical kitchen. And I would need 2 hydrogen molecules. Okay, got those, right? I need 1 oxygen. Boom, I got that. Okay, then I'm going to take this and I'm going to recombine these like this. And just like making cheese sandwiches, instead of making cheese sandwiches, I have made water. Okay, exact same process. Cheese, bread, we make a sandwich. Hydrogen, oxygen, we make water. Okay, same process. So, obviously this works with individual particles. Molecules, 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 okay? But what if I did this, okay? What if I multiplied all of these coefficients by 100? So if I had 200 hydrogen molecules and 100 oxygen molecules, is that still the same ratio as it was before? Grace, is it still the exact same ratio? Yes. And it's still the same ratio, but there's a huge caveat. If I multiply everything by the same number, okay? If I multiply hydrogen by 100, and if I multiply the oxygen by 5, then the ratio gets all screwed up, okay? Same thing with sandwiches, right? If I can have 10, 20, 10, same ratio, 1,000, 2,000, 1,000, as long as we multiply everything by the same number. And there's no limit to this. I can multiply by 1,000,000, okay? I could have 2 million hydrogens, 1 million oxygen, and 2 million water, right? Everybody's cool with it, same number, right? As long as it's the same number. Now, I'm gonna go big. I'm gonna go real big on my multiplication. I'm gonna multiply that 2 by Avogadro's number, 6.02 times 10 to the 23rd, hydrogen atoms. And then we're gonna have 6.02 times 10 to the 23rd oxygen. And then we're going to have 2 times Avogadro's number of water molecules. Okay? This is why I said everything goes full circle. Okay? Everything goes full circle that we've talked about. So if I have 6.02 times 10 to the 23rd oxygen molecules, miles, how many moles of oxygen molecules do I have?
1.
1. Oh. So this is saying this is 1 mole of oxygen. That's cool, right? So then how many moles of hydrogen am I going to have, Miles?
2.
2 moles of hydrogen. And then I can have 2 moles of water. So here's what I want you to see. Those coefficients represent 2 things. The ratio of individual particles, and they're a ratio of moles, okay? That's all they are, okay? It's a ratio of particles, there's a ratio of moles. Now, listen to me very carefully, okay? It is not a ratio of mass, right? This is not saying 2 grams of hydrogen react with 1 gram of oxygen to produce 2 grams of water, which doesn't make any sense at all anyway. Okay, does it? It's just, it doesn't. I can't take 2, react it with 1, and end up with 2. Okay? So listen to me very, very carefully. Okay? If you keep this in mind, stoichiometry is simple. These numbers are not, those coefficients are not a ratio of mass. Okay? It is a ratio of moles. That's it. Okay, it is only a ratio of moles. And the same thing is true of sandwiches. Okay, I'm not saying I'm going to take 1 pound of cheese and react that with 2 pounds of bread and get 1 pound of sandwiches. Okay, that doesn't make any sense. Like 1 pound and 2 pounds gets me 1 pound. Doesn't make any sense. Okay, so what's going to be important then, this is where mole conversions are going to play such a vital role with this, is that when you go from one reactant to another and you're doing a conversion, okay, you cannot work as a ratio of mass. You can work as a ratio of moles, but you cannot work as a ratio of mass. But the problem being, when we go into lab, what are the scales measuring? Man, scales measure in grams, they don't measure in moles. So what do you think we're going to have to do a lot of? Mole conversions. Okay, right? But we can do that. This is not a problem. So let's go back to making water. Okay, let's go back to making water. So Coot, I want you to make 10 moles of water. You go, great, Mr. Burkamp, that's cool. I want you to make 10 moles of water. How many moles of hydrogen are you going to need to make 10 moles of water? Why? Your answer is right.
The amount of water and the amount of hydrogen are the same?
Substitute, instead of amount, put in the word moles.
The number of moles of hydrogen and the number of moles of water are the same?
Which means we're in a 1-to-1 ratio, okay? So this is how stoichiometry works. Keaton sits here, he goes, right, Mr. Burkamp, I can play your game. I see how this is going to go. I want to make 10 moles of water. Cool. So you come up here, and you look in front of the water. Oh, there's 2 moles of water. Guess what? In front of the hydrogen, there's a 2. The moles cancel out. What are you left with? Moles of hydrogen. 2 divided by 2 is 1. 1 times 10 is 10. So what that means is that if I want to make 10 moles of water, guess what? I'm going to have 10 moles of hydrogen. Now, Grace, this is how many moles of hydrogen I've got to give Keaton to make his water. You have to figure out how many moles of oxygen am I going to need. So how many moles of oxygen are you going to need to make 2 moles of water?
Would be like a third of that one.
About a third. It's either going to be a half or it's going to be twice. Now, that's great. So we're going to follow that same thought process, right? You want to make 10 moles of water. True? So this is the honest to God's truth. Whatever units you have here is what you put down here. There's no exceptions. 0, zip, none. No exceptions whatsoever. Okay? I got 10 moles of water here. What am I going to put down here?
Water.
Moles of water, right? I'll put moles of water. Now, Grace, you're trying to figure out moles of oxygen, right? Okay? So, what's the coefficient in front of the water?
2.
What's in front of the oxygen? 1, right? Okay, so if you go scroll up a little bit, there's the 1 in front of the oxygen. So that means there's a 2-to-1 ratio. So my moles of water are going to cancel out. I'm going to take 10 and divide that by 2. I'm going to get 5 moles of oxygen. Okay? Got that? Pretty simple. Now, let's say that, here's the other way this can play out. Let's go back to the sandwich analogy. Okay? Go back to the sandwich analogy. Ethan, I'm going to give you 20 slices of bread. Okay? How many slices of cheese are you going to need to go with that 20 slices of bread?
10.
How'd you get that?
Well, you need 2 slices of bread to make a sandwich, and so you just cut that in half.
Divide by 2,
Yeah.
right? So here's the other thing. You could work with on the same side, too. Okay? It's like an infomercial. Well, wait, there's more. For an additional $10.99 shipping and handling, here's what else you can do. You can work everything within the same side. You don't even have to cross between products and reactants. You can stay within the same thing. You can go, oh, I got 20 slices of bread. For every 2 slices of bread, there's 1 slice of cheese. The bread cancels out. I get 10 slices of cheese. So you can even do ratios with products. You can do ratios with reactants. You can do 2 products. You can do 2 reactants. You can have products and work backwards to reactants. You can start with reactants and end up in products. The options are limitless, but it's always the same process, okay? So here's the deal. On any problem you're going to do, there's a certain sequence of things that you have to have. First and foremost, the most important thing is that you have to have the balanced equation, okay? Because if you don't have the balanced equation that's right, you don't know what the coefficients are. Okay? If you don't know what the coefficients are and subscripts and everything else, then you're dead in the water. So that's why I said it is so vital that you have the correct balanced equation. Because if that's wrong, everything's going to go wrong. Okay? So let's say, then from there, then you can look at simply mole to mole conversions. Okay? And that's what we're going to start off with, and that's what we've been doing. Okay? It's just mole to mole conversion. Okay? And then eventually we're going to add to this. Now, here's the deal. Y'all remember mole's mole. Okay? When we started doing conversions, we had the mole. Okay? And we're going to branch out. It's going to look like a little starship, but okay. So here was mass, parts, mass, parts, moles, moles. So now, basically what we've done is that we've added another mole to it, okay? We've added a different type of mole, but it's the exact same process. So does anybody remember, if you hearken back, if you were doing, let's just say, pretend that none of this exists. We'll get back to this, okay? We'll get back to this. I said, hey, I'm going to give you 24 grams of carbon, okay? So, Parker, I'm going to give you 24 grams of carbon. I want you to figure out how many moles that is. So what are you going to do?
Take that divided by the molar mass of carbon.
So the molar mass of carbon is 12.0 grams of carbon per 1 mole. Okay? Grams of carbon cancel out. He got 2 moles. So what you did is that you started up here in mass, and you ended up down here in moles, and you divided, and you looked at the periodic table. Okay? Old school. Old hat, right? Relative atomic mass of carbon is 12. Boom, here you go. I got 24 grams, so that means that I got 2 moles. So if you're going from mass to moles, you got to look at the periodic table, right? Now, if you're over here in parts, right? If I give you 12.12 to 12.04 times 10 to the 23rd atoms of carbon, okay? And I want to know how many moles that is. In 1 mole of carbon, how many atoms are there? Or 1 mole of anything, how many particles are there?
6.02.
6.02 times
10 to the 23rd.
times 10 to the 23rd, right? So if you're dealing with parts, you use the avocado stand. You go, oh, right, 6.02 times 10 to the 23rd. Okay. So if you're on this side, go away. If you're on this side over here, you're going to use the avocado stand. 6.02 times 10 to the 23rd. So if you're in mass, you go to moles. If you're in parts, you go to moles. Now, here's what's important about this, okay? Listen to me, listen to me, listen to me, listen to me, listen to me. If you were to go from one type of moles to the other, the only way that you can do that is by looking at chemical equations. So here's what I want you to see, is that there is no way to go directly from one type of mass to another type of mass. It is not allowed. On this path, you can start with mass, you can go to moles, and you're going to look at the periodic table. Oh, that's going to convert that into moles. Then you're going to go from one type of mole to another, okay? And then you're going to look at the chemical equation. And then when you get over here, you might say, oh, how much mass do I need? Oh, I'm going to go up this way. Oh, I'm going to look at the periodic table. Oh, I'm going to go that way. I'm going to look at the avocado stand. I want to use Avogadro's number. So this is all about the sequence, okay? And if you want to draw this out, it's cool, okay? Some people like this visual approach. But here's what I want you to see. There's no way to go from here to there. Can't do it. You can go from mass to moles, you can go from moles to moles, and then you can go to mass. I can start with going, hey, we're going to make water. I'm going to give Addie a certain number of particles. I want to know how many grams of water she can produce out of that. All right, this is for chemical. I'm going to go from moles, parts into moles, moles to another type of moles using the chemical equation. Boom, there you go. So literally, this is all about sequence. So all we've done so far is we've talked about just mole to moles. Oh, okay, right. We're just going to look at the chemical equation. But if we branch out to this, here's the deal. Depending upon where you want to start, you might start with moles here and work backwards over here to moles and end up with mass. You might start up here with parts, go to moles, end up with another type of moles over there, okay? Some people really like this visual approach, but here's the most important thing you have to understand, okay? The one step you will always use, no matter what, you will always do a mole-to-mole conversion based upon the chemical equation, okay? That is the one thing that is always true. You might not involve mass, you might not involve parts, you might not involve any number of things. But what is always true, at the core end of the day, every stoichiometry problem goes from a mole-to-mole conversion and you look at the chemical equation. You might not use the periodic table, you might not use Avogadro's number, but you will always do a mole-to-mole conversion because the coefficients represent moles and they don't represent mass. So, step it up a little bit, okay? So we're going to go back to making water, right? 2 hydrogens plus O2 yields 2 water. Okay, so I'm gonna take a balloon, right? And I'm gonna fill up the balloon with 4 grams of hydrogen. Okay? And I'm gonna have 4 grams of hydrogen. And I want to know how many moles of water I can produce from 4 grams of hydrogen. Okay? Because like the scale measures in grams. I take the balloon, I fill it up with hydrogen, I put it on the scale, it goes, oh, that's 4 grams. I want to know how many moles of water. Now, if you are a visual person, here's what you have to realize. You're starting up here in mass. I've given you 4 grams of hydrogen. So what are you going to have to do with that 4 grams of hydrogen? Convert it first into moles of hydrogen or oxygen or water? Huh? Hydrogen. I can only convert it into moles of hydrogen. Okay, I can't do anything else. So I'm going to take the 4 grams of hydrogen, convert that into moles of hydrogen, and then I'm going to take moles of hydrogen, convert it into moles of water. Okay? So, there you go. So, I'm going to start here. I'm going to look at the periodic table. I'm going to look at the chemical equation, and I'm going to end up over there. I'm going to cross that bridge. Some people like this analogy, like this is a bridge that connects the two. And whenever you cross the bridge, you look at the chemical equation. So here's what you're going to do, just like you've done before. Oh. So I'm going to start with 4 grams of hydrogen. Okay? Why do I put the H2 on the end of it? Carter, why did I put that H2 on the end of the hydrogen? Yes. So what? Rhymes with iatomic. It's diatomic, right? There's a whole bunch of things you got to keep track of. It's like, oh, hydrogen's diatomic, right? Got to remember that part, okay? So don't think, oh, we've taken the equations test. I don't need to worry about diatomics anymore. No, horrible, okay? So I got 4 grams of hydrogen. Now, here is your absolute process, okay? And some people like a fill in the blank kind of thing, okay? So up here in the top left, you always start off with what you're given. Okay, that's it. It could be grams, it could be moles, it could be particles. Okay, this is what you're given. Now, here's the absolute rule, and there's no exceptions to this whatsoever. Whatever units you have here is what you put there. That's it. Okay? So I got grams of hydrogen, so I'm going to put grams of hydrogen up there. That's it. Okay? That's it. It's the only thing I can do. Never, ever, 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 ever will I put grams of hydrogen there and put moles of hydrogen here. I will never put grams of hydrogen up there and put moles of water down here. I will never put grams of hydrogen up there and put grams of water here. Or grams of hydrogen and moles of squirrels. Okay? No. But if you keep that in mind, Stoic problems aren't difficult. Okay? It's when you don't write down labels. Honest to God, I will have no sympathy for you. So come into this work camp, I don't know what I'm doing. Here's what I'm going to ask you. Have you written down the units? If you say no, at that point I refuse to help you. Okay? I'm not going to. I am not going to help you. Okay? And I'm not being a jerk. It's because of the fact that you don't know what the units are. And if you don't know what the units are, you can't do the mole conversions. Okay? So every problem is going to start the same way. I'm going to give you something. It might be moles, it might be grams, it might be particles. Okay? So I'm going to give you something. And whatever I give you up here is what you start with up there. And then you put those same units down here. There is no exceptions. Zero, zip. I'm not going to say, well, sometimes you're going to do, no. Okay? There is no sometimes. It's like, well, there's no wells. Whatever units you have here is what you put here. No exceptions. Zero, zip, none. Okay? So, but I need a conversion that involves moles, because that's what I got to end up in. So I know if I look on my periodic table, because hydrogen is diatomic and the relative atomic mass of hydrogen is 1, so if I have 2 of them, oh, that's 2 grams. And that's going to be 1 mole of hydrogen. Now, if I stop right now, if I don't do any other conversions, I stop right here, right now. It's like I'm done. Can't do it anymore, I'm going to stop. What units would I have? What about it? I'm on grams of hydrogen, moles of hydrogen, parts of hydrogen.
Moles of hydrogen.
If I do nothing else, if I stop right here, grams of hydrogen cancel out, I know I'm going to have 2 moles of hydrogen. Okay? But that's not what I want. I want to end up in moles of water. Okay? Now, again, if you're a visual person, here's what we did. We started up here at 4 grams of hydrogen. We looked at the periodic table. We said, oh, periodic table, 2 grams of hydrogen per 1 mole. Right now, I am at moles of water. Or moles of hydrogen. Now, at this point, I'm going to go, oh, I'm going to go from here over to here. Cool. Where am I going to look? Oh, the balanced chemical equation. So again, if you're a visual person and you want to use this to keep track of where you are and where you're going to look to find your information, hey, cool, go with this. It's wonderful. This is why I have it up there. Okay? If you're just, Mr. Burkamp, I'm a units kind of person, I'm happy for you. Okay? It's cool, right? Be the unit. Okay? It's cool. It works. Okay? So then come down here and go, okay, right. I got moles of hydrogen here. Now here again, here's the rule. Whatever units you have here is what you're going to put down here. Oh, I have moles of hydrogen. I'm going to put moles of hydrogen here. I am not going to put moles of water. I'm not going to put moles of goats. I'm not going to put moles of electrons. The only thing I'm going to put down here is moles of hydrogen. That's it. There is no exceptions. Okay, this is the beauty of this. There is no exceptions. Whatever units you have here is what you put in the bottom right of the next cell. 0, zip, none. Oh, moles of hydrogen. I'm going to put moles of hydrogen down here. Now, oh, what's a conversion that I could use? Oh, we're talking about water. I want to put moles of water up here. That's cool, right? So, now I'm going to look at my balanced chemical equation. Oh, in front of the hydrogen, there's a 2. I'm going to put a 2 there. Okay. Then I'm going to look at the water. Oh, there's a 2 up there. That's cool. So at this point, The 2's cancel out because that's basically a 1-to-1 ratio. I've taken 4 and divided that by 2. I get 2 moles of water. So if I start with 4 grams of hydrogen, okay, I can produce 2 moles of water. Okay? Got that. There you go. That's it. As complicated as it gets. Now, this is why this is a ratio of moles. Now, I'm going to change it up. Instead of 2 moles of 4 grams of hydrogen, I'm going to give you 4 grams of oxygen. Okay? It's the exact same mass. But this is what I want you to see is important in terms of the difference. I want to give you 4 grams of oxygen, and I want to know how many moles of water I can produce. Okay? That's what I got. So, it's the exact same process. I have grams of oxygen here. I'm going to put grams of oxygen down here. No exceptions. 0 zip. Grams of oxygen, grams of oxygen. I'm going to look at the periodic table because I got to get down into the moles. Got to get funky with the moles. So I'm going to put moles here, right? Alk grill. How many grams of oxygen, being diatomic, are there in 1 mole of oxygen?
16,
Times 2 is
32.
32. So that's 32 grams of oxygen, okay? Because one oxygen by itself is 16, is diatomic. Boom, I double it up, I get 32. So if I stop right now, just think about this. If I stop right now, do I have more than a mole of oxygen or less than a mole of oxygen? Ella. Do I have more than a mole or less than a mole?
More. Less.
Less. Because I'd have to have 32 grams to have an entire mole, right? I only have 4 grams.
Yeah.
So I have a lot less, right? I have a lot less than 1 mole of oxygen, right? Because I'd have to have 32, I only have 4, right? Okay. Now, follow the sequence. I have moles of oxygen here, which means I'm going to put moles of oxygen down there. Okay? It's cool. It's the exact same process. No exceptions. Units, 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 units. Boom, there you go. Now, at this point, I'm going to cross the bridge. I'm going to go to the chemical reaction. Oh, right. My ratio here, when I look at my balanced equation for water, is between oxygen and water, there's a 1-to-2 ratio. Oh, okay. So I'm going to come down here, and in front of the oxygen, there's a 1. In front of the water, there's a 2. Boom. That cancels that out. So, in this situation, here's what you want to do. You can take 4. What I would recommend, depending on how you want to handle the math, you can take 4 times 1 times 2, otherwise known as 8, and then you divide that by everything on the bottom, which in this case is just going to be 32. Okay? So, if you take 4 times 8, or 4 times 2, you get 8. 8 divided by 32 is 1/4, which is 0.25. So out of this, I get 0.25 moles of water. So here's what I want you to see. Okay, and this is why I did this. Even though I started with the same number of grams, so 4 grams of hydrogen is capable of producing 2 moles of water. Okay? But 4 grams of oxygen can only produce 0.25 moles of water. Okay? So even though I'm starting with the same mass, I can produce completely different quantities of water. Now, here's the reason why. Okay? So pretend that this problem doesn't exist. Okay? We're going to make cars. Okay? It's a horrible car, but you get the point. And we're going to have 1,000 pounds of tires, and we're gonna have 1,000 pounds of the car itself, okay, without the tires. Okay, so I have 1,000 pounds of the metal, the seat, the car itself, and I have 1,000 pounds of tires. Okay? Obviously, if I have 1,000 pounds of tires, I can make a lot of tires. Excuse me, I can produce a lot of cars because each tire doesn't weigh very much. So if I have 1,000 pounds of tires, oh, I can make a lot of cars. But if I have 1,000 pounds of the car itself, that might only be one car. So even though I have the same mass, 1,000 pounds of tires is going to make me a completely different number of cars than 1,000 pounds of metal. Okay? This is why you do the conversion from moles to moles. Got the idea? Okay, so stop that, stand up, take a stretch. All right, so let's make sure everybody's cool with what you've got going. Now, on every one of these reactions, I've chosen reactions that you all are familiar with, okay? So the first one, you're going to drop a piece of sodium in with water, you're going to produce sodium hydroxide and hydrogen gas, you're going to produce a base, and turn it purple, okay? So, let's start off with number 3. I'm going to show you exactly how I want this done. So I don't know how many moles of sodium are required to produce 4 moles of hydrogen gas. So that's your task. I say, okay, hey, here's the deal. Class, we need to make 4 moles of hydrogen gas. Okay?
No.
So here's your reaction. 2 Na plus 2 waters is going to yield 2 NaOH plus hydrogen gas. It's already balanced for you. You don't have to balance it. It's already balanced. Okay? Merry Christmas. So I want to produce 4 moles of hydrogen gas. Okay? So this is what I want to end up with. I want to produce hydrogen gas. So the question being is that how many moles of sodium am I going to have to produce this? Now, here's the deal. Here's what you're tempted to do. Y'all are tempted to work this problem left to right because that's how the equation reads. And you're tempted to go, oh, I'm going to start with the sodium. Okay? No, 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 no. Okay? Just like the sandwich analogy. If I said, hey, I want to make 20 sandwiches. How many slices of cheese am I going to need? 20. Okay? That was in the reverse direction. The same thing is going to happen here. We're just going to kind of work in the reverse direction. So, here's the deal. I want to produce 4 moles of hydrogen gas. Okay? So don't flip out and go, oh, but that's on the product side. You're right, it is, but this is what we have to start with. Your conversion is always going to start with what you're given. Okay, so I want to put 4 moles of hydrogen gas. Now, again, here's the rule. Whatever units I have here is whatever I put down there. And the worst thing that you can do, I'm telling you, the worst thing you can do is be teenagers and go, oh, Burkham's old, okay, wears his tie and a shirt. I don't need to follow Burkham's advice. We're teenagers. We're smarter than he is. We know shortcuts, okay? No! If you look at my answer keys, and I've done this longer than you all have been on this earth, if you look at my answer keys, I still write all of these out. You know why? Because it works.
Because you're old.
Well, that too, okay? And it works. If there was a shortcut method to do this, I would teach you the shortcut method right from the get-go, okay? But there isn't. So, I got 4 moles of hydrogen. I'm going to put moles of hydrogen down here. And in this case, I want to figure out moles of sodium. Okay? Now I know my ratio. Whatever units I have here is what I put down here. Then I figure out what do I want to convert that into. Oh, sodium. Now I look at my balanced equation. Oh, in front of the hydrogen, there's a 1. In front of the sodium, there's a 2. So I take this 2, boink, put that there. 1, boom, put that there. I multiply 4 by 2, check my math, I get 8 moles of sodium. So what that means is that I need twice the moles of sodium as I do of hydrogen, because oddly enough, there's a 2-to-1 ratio. Okay? That's it, all you have to have. Now, on number 4, okay, that was number 3, get number 4. How many moles of water needed to react with 5.5 moles of sodium? So it's the exact same process. Oh, I'm going to put 5.5 moles of sodium. Whatever units I have up top, I put down below. So I'm going to put moles of sodium here, and then the question asked me for moles of water. Now I know my ratio, and then I'm going to come up here and go, oh, in front of the sodium, there's a 2. In front of the water, there is also a 2. So that basically reduces down to 1. So I get 5.5 moles of water. Okay? So, try number 5 on your own. Now, everybody cool. So Raman, what did you get for your answer to number 5? Beautiful. There's a 1-to-1 ratio. Okay? Now, you got a combustion reaction. Eight moles of carbon dioxide and 10 of water. Okay? Same process. Okay? Just different equation. Now this is a little bit more complicated because none of these are in a 1-to-1 ratio. Okay? All of these have different ratios, a 2, a 13, an 8, and a 10. Okay? So now I kind of stepped it up a little bit more. It's the exact same process, okay? But now the numbers aren't going to work out as nicely. That's all. But it's the exact same process. Oh, I have 0.8 moles of butane, C4H10, okay? But it's the exact same process. I'm going to put moles of C4H10 down here. And in this case, I want moles of oxygen. Okay, that's cool. Now I go in front of the C4H10. There's a 2 there. In front of the oxygen, there's a 13. So the math is just a little bit more complicated. So now I'm just going to take 0.8 times 13 and divide that by 2. So what do you get?
5.2.
What'd you get?
5.2.
5.2 moles of oxygen. Okay? Well, there you go. Okay, so try 8 and 9. Yep.
On number 8, when it says 2.4 moles of oxygen, is that O2 or just O?
Yeah, that's that O2.
Okay,
Yeah. It's oxygen gas.
yeah, thank you.
So it's still that same ratio of, you're going to use 13, and with the water, you're going to put 10. Okay, now, let's talk about this next reaction. This next reaction is what's known as a thermite reaction. And even though 10 is a single displacement reaction, 10 is one of the very, very few single displacement reactions that can happen with solids, okay? So, this is what I'm gonna show you right here. So here I have a rusted iron ball bearing. And I have another one wrapped in aluminum, okay? So this is basically what I'm going to do right here is this reaction. So what's going to happen, I'm going to hit these together. And when I hit them together, what's going to happen is that the aluminum is going to go in and it's going to swap places with an iron atom. And so out of that, I'm going to get aluminum oxide and iron, okay? So, but if I don't hit them hard enough, okay, and this is this idea of activation energy, if I don't hit them hard enough, the reaction won't start because I'm not getting the thing up the roller coaster, up that initial hill, okay? But if I hit them hard enough, then I start a reaction. But I have to hit it hard enough. Now, what do you notice that also comes out of this reaction?
Sparks.
Sparks. You get energy, right? So what that tells me is that this product over here, that aluminum oxide and iron, is at a lower energy state than where I started, okay? So this is a very exothermic reaction. And if you see this going like on large scale where you have a whole bunch of this, it's called a reaction with thermite, then it gets very, 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 very hot. Okay, so here's the deal. So that's the reaction. It's a single displacement reaction. It's one of the very, very few single displacement reactions that can happen without a solution. It can happen with solids. So, on number 10, here's the deal. How many moles of aluminum oxide can produce from 81 grams of aluminum? So, you're given 81 grams of aluminum, okay? You start with that. Now, this is where this is going to get a little bit more complicated. Because on moles of mol, everything that we have done up to this point has been from here over to here, okay? That's the only thing we've done. But now, so we're going to step up the game a little bit. So now I'm going to start up there with grams of aluminum, okay? But it's the exact same process. Here's what I want you to see, okay? It's most vital. You want to go from grams of aluminum into aluminum oxide. So here's what's important. I cannot go from grams of aluminum straight over here to moles of aluminum oxide. Okay, can't do it. Okay, I cannot go from here to here. But what I can do is I can go from grams of aluminum into moles of aluminum. And then I can go from moles of aluminum to moles of aluminum oxide. Okay, but I cannot go directly from here over to here. Can't do it. Okay, this is why you have to think this through. So, in this situation, I've got 81 grams of aluminum. What's the molar mass of aluminum?
26.98.
So we'll just call it 27.0. Okay? Okay? Now, here's the deal. Again, I got grams of aluminum. The only thing I can put down here are grams of aluminum. That's it. That's all I can do. Grams of aluminum, grams of aluminum. That's it. Okay? I can't do grams of aluminum oxide. I can only go grams of aluminum into grams of aluminum. I'm going to look at the periodic table, which I did. Now, here's what's important. How many moles are equivalent to 1 gram of aluminum? If I measure out exactly 27 grams, how many moles is that? 1, exactly 1. This is exactly 1 mole of aluminum. Now, here's a common misconception. This 1 here is a 1 there because 1 gram or 27 grams of aluminum is only equal to 1 mole. This 1 is not a 1 because of the coefficient up there, okay? This is only going to be 27 grams is exactly equal to 1 mole. So this 1 is here, not because of what's up there, okay? So don't think that. Now I can look at my periodic table. So again, and here's the rule. I got moles of aluminum here. I got moles of aluminum here. Now, stop. Now, let's just step back. Step back. Do I have more than 1 mole of aluminum or less than 1 mole of aluminum? More than 1 or less than 1?
More.
More than 1. Why?
Because 81's bigger than 27.
Yeah, 81 is bigger than 27. So I know I'm going to have more than 1 mole of aluminum, right? So if I stop right now, if I don't do anything else, I have moles of aluminum. Okay? So what that tells me is that I've gotten into one side of the mole. Now I need to go from one type of mole to another type of mole. Oh, okay. So in this case, you're asked to figure out how many moles of aluminum oxide. So now I'm going to put moles of aluminum oxide up here. Now I'm going to look at the periodic table. Excuse me, now I'm going to look at my balanced equation. So in front of the aluminum, there's a 1. In front of the aluminum oxide, there's, in front of there's a 2. I wrote that down wrong. There's a 2 there. There's a 2 in front of the aluminum. My bad. It's like, oh, that's something wrong. So I got 2 and then 1 mole. Okay? So here's what you're going to do. And you have to be careful about how you sequence this into your calculator. You're going to take 81 times 1 times 1, otherwise known as 81. What you have to be careful of, when you punch this into your calculator, you can't punch in 81 divided by 27 times 2. Because what it's going to do is it's going to multiply, it's going to divide by 27, and then it's going to multiply by 2. You have to put this in brackets so that you're in effect dividing by 54. Okay? So, if you're going to do this, you can do it all in one step. Your calculators do wonderful things. That's just going to be 81 divided by 27 times 2. So put that 27 times 2 in brackets so that your calculator does the correct order of operations. So, what do you get as an answer?
1.5.
Exactly?
Yeah.
Exact 1.5. So we're going to write that as 1.50. Now, of aluminum oxide. Okay? So, when you look at this, notice that every answer that I've given you, or every value that I've given you, has at least what we call 3 significant digits, which means your answers need to have at least 3. So if this had been like 2, just don't write down 2. You'd have to write that as 2.00. So, you're on your own. Do tomorrow.